Okay, so I'm going to talk about IO monads and specifically error management in applications that use IO monads to model their computations. Before we dig in, here's a few words about myself. So my name is Guillaume Bogard. I come from France and I work for a small consultancy as a Scala developer. And apart from that, I love functional programming, roller coasters, and strategy games. And I also happen to have a website on which I like to blog, but not as often as I would like to. All right. So the main topic of this talk is IO monads. But before we talk about that, I feel like we might use a very quick recap on what are monads. So I'm going to attempt a very simple definition, which is far from being perfect and is missing some stuff, but it conveys the important ideas that will be useful for the rest of this talk. So a monad, M of A, is an immutable data structure that you use to describe the computation of some values of type A. And a monad has some important parts. One of these important parts is the ability to turn a value into a monadic context using a type constructor, which is often called pure. And monads, they have the ability to compose, to change computations that depend on one another. So you can use them to create more complex programs out of smaller programs. And they describe some effect or some behavior. So you use monad to sort of enrich your computation with a behavior or model some behavior such as optionality or asynchronism. And that behavior is reflected in the type signature of your function or value. The ability to describe this behavior using the monad means that not only you can compose them, because that's the essence of monads, but the effect is now part of the type signature. So not only do you know about it as a developer, but also the compiler knows about it. That's why when we introduce Scala to people from the outside world, and we talk about the option monad, without calling it monad often. One of the main benefits of a data structure such as the option monad is that since the compiler knows about it, it won't let you compose optional values with non-optional values without some explicit lifting into some monadic context. In that case, option. Hope that makes sense. And so the IO monad is one type of monad that also is used to encode some behavior. And that behavior is the ability to encode an asynchronous program as a pure value. So they are used to turn some computation into a lazily evaluated program, a referentially transparent value that you can pass around, pass as parameters to other functions, or define in pretty much any order without fear of your side effect being executed you wanting that. All right. Excuse me. And IO monads, they are used to reveal the presence of side effects. They reveal the presence of side effects. It doesn't mean that the side effect is totally going away, because at some point when you run the program, of course, the effects such as connecting to an external service or printing to the standard output are going to be run. But the very fact that we can encode these effects in some particular structure means that we can immediately identify which part of the code are potentially dangerous because they rely on some external service or some undeterministic code. And just like any monad, they compose with the flat map method. So if you have a program to get a user and a program to get the pet of a user, by composing these two programs, you are able to get a pet from the ID of a user. So again, that's the idea of modeling computations that depend on one another. And when things go wrong, because they always do, the IO monads, as it is defined in Katz effect, has some error handling capacities, namely the capacity of raising errors, raising throwables inside the context of the IO monad, and the ability to recover them later. So here is an example of that. I'm just raising an exception. You see that I get back a value of type IO of int, and then I can call recover on that, recover with on that value, and I have a small pattern matching expression that I can use to handle my error the way that I want. So for the rest of this talk, I'd like to model a particular use case, which is an authentication method. Very simple method. I want to be able to authenticate a user using some name and some password and return the user's information. And to implement that sort of method, we actually depend on lots of things. So we need to find the user information from an external source, such as a database, an external database. But we also need to implement maybe some business rules. We need to make sure that the password is right. Maybe we have rules such as we want to check that the user also has a valid subscription. And let's say one more rule, the user must not be banned from our service. So to model that authentication method, I'm going to split it into several programs that will enforce each of these rules and then compose these programs to form a bigger one. And I will start by modeling the various errors that can happen. So I'm modeling the errors using case objects or case classes that all extends from runtime exception, because you can only raise values that are throwables. So in that case, I use runtime exceptions. And once I have modeled all of these errors, I will define my small specific programs without implementing them. I will be only interested in the type signatures for the rest of the talk. And once I have these programs that each enforce one of the rules that I have mentioned, I can compose them using for comprehension, which is just syntactic sugar for flat map. And I have a full program that takes a username and a password as an input, checks all the rules that I want to check, and returns the information of my user if everything goes well. And if one of these programs fails along the way, then I will get back a failed IO with the first error that has occurred in the composition. Okay, so that's the full defining error case in the specific programs, and then we compose these smaller programs to solve the bigger problem. So it's looking good so far, but here's an example of how one would use this function. We pass some parameter, then there is an IO that we want to execute when everything goes well, and then there is maybe a bunch of IOs that we want to execute for each of the various error case that can happen. So it's looking good, but there is some issues with that approach. Maybe you get a feel of what these issues are by looking at at the code that I have just shown, but it turns out I can go back. All right, it's fine. So the first issue is that exceptions are invisible in the sense that they don't appear anywhere in the type signature of my method. When I say that I will yield a value of type user, when I say that the return type of my function is IO of user, I don't say anything about the possible error case that might happen. And since they are invisible, then one can simply forget to recover them. And if you don't want that to happen, then you need to explicitly document them, which is kind of the same situation as regular Java code, where you need to have these throws annotations in the comments to know that these methods are not safe to use. So if you don't recover the error, then it is propagated across all the IOs that you will compose as part of your program until it is recovered eventually. And then the last issue, not quite the last. Another issue is that throwables are a bit ambiguous because, again, they don't appear anywhere in the type signature, and there is no way to distinguish using only the type system between something that is purely a technical error, such as timeout exception, or something that is my own authentication exception that is part of my business logic. And the last error is that you get no proper exhaustivity check for these exceptions. So that was the case on the code that I have shown before. When you open a recover with block, you are forced to have an exhaustive match expression. You are forced to have a case underscore where you just define what will happen if the exception is known of what you have defined. All right, so that's the various issues with that approach. To summarize, when I see a type signature that looks like this, it is kind of a lie because the type signature does not convey anything about the possible error case. It says that I will get a user at some point, but it doesn't say anything about what will I get if something goes wrong. So it requires more reading and more testing. And if you forget to recover the error, it will be propagated across the entire composition and maybe the entire application. Okay, so how can we make that better? Well, my take on the subject is that while exceptions serve some purpose, maybe we shouldn't use them to model business rules. Maybe we should use them in a very restricted area, such as, so that exceptions are not used everywhere, but only in exceptional places, in places where we actually want to fail. And that is the point that I will try to make during the rest of this talk. So my take on the subject is that domain errors that are part of your core logic, should not be modeled as exceptions, but rather as algebraic data types. So domain errors are not quite like technical errors because domain errors are documented edge cases that has forgotten their password is very, very common. And it's not something that is worth modeling using an exception and logging and that sort of stuff. On the other hand, exceptions, they can serve a purpose, especially because since exceptions by default, when they are not recovered, will possibly make the whole application fail. They can be used to model fatal errors such as I cannot reach a database and I need a database to be able to run. And that is an error that is not part of the core logic, but is a purely technical error that you might want to notify your developers team about. So as a general rule, when a user is breaking one of the business rules, maybe you don't need to fail in the sense that you don't want to crash the entire application or take the risk of not recovering the error, because these are just part of the user experience. But when you want to fail, when you need to fail for some fatal flaw, such as you absolutely depend on that external service that is down at the moment, you probably want to fail fast. So in some cases, and this is what I mean by exception server purpose, in some cases you want the application to fail fast so you get immediate response from the developers team. And you don't want to handle business rules in the same way that you handle technical errors, because you don't want to expose technical errors to your users. And the other way around can be true, because you don't want to have thousands of logs about things that are just completely common, such as a user forgetting the password. So you don't want your users to know about your technical errors, and maybe you don't want your developers to know about actions that are taken by your users and are completely normal. All right. I see no questions so far. I hope everything is clear. So, as I said, instead of using exceptions to model our various business rules or edge cases, I will use a subtype. So I define this trait called authentication error, and then all the objects that inherit from this trait are my various authentication errors, such as the password is not correct or the user has been banned. And once I have done this, I can rewrite the signature of my authenticate method to return not only a user anymore, but an either, which is either an authentication error or a user. And this either is wrapped in an IO. So here we have nested monads. Each of these monads encode a specific effect or specific behavior. Either is here to encode the effect of failure, and IO is here to encode the effect of asynchronism. And just by doing that, we have achieved some of the goals that I wanted us to achieve in the first place. So side effects are obvious in the sense that they appear in the type signature because we are still using IO. But also the main errors are visible, and they weren't before, but now they appear also in the type signature, and they cannot be forgotten. Because as they appear in the type signature, then you know about them, and the compiler knows about them too. So there's no way for you to just forget to handle them. The compiler would not allow it. Technical errors can still be raised and recovered because we have nested the two monads, but we still have the error channels from both monads. So we can use the either for our domain errors, which are the most common, and we can still raise exceptions in the IO context if we need to model fatal technical errors. And so we don't need to check the documentation for edge cases that we would have forgotten. And we have clearly two distinct error families, technical errors and domain errors, just by doing that. But we have also something very important. When we rewrote the type signature to use nested monads, we have lost the ability to compose these programs into a bigger one. So this nice example here does not compile. And if I want to write, if I want to compose I nested IOs and either together to create a bigger program out of smaller programs, then I need something like this. I could write an authenticate method, and and this is a code that does what I want and compiles. But I think we can all agree that error handling shouldn't be this painful. This code is pretty ugly for code that is just composing some business rules and authenticating the user. And so what can we do about it? Turns out there is a solution to that. And that solution is called a monad transformer, which, and I'm sorry to disappoint you, has nothing to do with transformers, but I just like the GIF. So monad transformers, there are type constructors that take monads as an argument and return a monad. So you have a monad and you have a monad transformer, and when you combine the two, what you get is another monad that encodes, that has the two effects that you wanted to compose. So another way to say it is that they add a behavior to some monad, and they give you a monad back so that you can have the two effects that you wanted to encode and still preserve the ability to compose your program, to compose smaller programs to create bigger ones. So in CATS, there is, for example, the option T monad transformer, which takes a monad F and adds the effect of optionality to it. And there is also a monad transformer called either T, which we are going to be using. And either T takes a monad F and adds the effect of failure to that monad. And one way to look at it is that either T is a simple wrapper around F of either, some monad containing an either. But instead of having two nested monadic contexts, which you need to unwrap specifically, you have only one monad that you can compose directly in a for comprehension. And there is this bidirectional transformation between F of either and either T, which is highlighted in this diagram. So when you have an F of either with some left and some right, you pass it to either T and you pass it to the either T.apply method, and it gives you that either T structure. And when you call dot value, the value method on an either T, it gives you back the nested monad that you had in the beginning. So it's really just this wrapper that is roughly equivalent with nested monads, but with the ability to compose them. And now that we know this, we are able to rewrite once again our authentication method, starting with the more specific programs. So I have changed the signature from IO of either to either T. And now I can use that as part of my authenticate method in my for comprehension, and everything compiles just fine. And I have this elegant program that is made of smaller specialized program. And just like IO withdrawables, an either T will short circuit computation on the first error. So you have, just like Mark put it this morning, you have a happy path, which is if everything goes well, you get a user in the end, or you get an either T containing your user on the right side, and if something goes wrong along the way, then you get the first encountered error. And this is a pattern that is sometimes referred to as railway-oriented programming, this idea of short-circuiting computation in F# and for fun and profit, for people that know F#. All right. So here's a full code snippet. And another way to do it would be, instead of rewriting the method signature of the specialized programs, you keep it as they were, that is an either in an IO, but then you use either T inside a composition when you actually need to compose. So instead of exposing the either t in the type signature of all your methods, you expose it only when you need it. In fact, you could also not expose it at all and have this authenticate method returning only a IO of either. And in the end of your composition, make a call to the value method, and this method will give you back a nested monad instead of an either t. So maybe it's good practice not to expose monad transformers everywhere, but only use them when you need them, because they come with a slight overhead. All right, so by using monad transformers, we have met all of our goals. We have clearly visible side effects like before. We have the ability to compose, to create our program out of smaller programs. We still have the benefit of having two distinct error channels, the one from purely technical failures and can raise only exceptions, only throwables, and the left from our either, which is the most common because it is used for business-related errors. And by having those two things, we can have two ways of handling these errors. We can choose to fail fast on fatal technical failures and still have the ability to provide good feedback to the user when we have a business edge case. All right, so now that we have met all of our goals, maybe just have a drink. Except I'm not going to do that because we haven't quite finished yet. Right, this talk has CATS-MTL in the title, but we haven't talked about it yet. But we could stop there. My point is that when you have these monad transformers, you can model pretty much everything with them, and they cover most of what you need to be able to write programs and handle errors in them. But there are still a couple of challenges that you may face and that you might want to address. One of these challenges is, what if we want nested transformers? Right, before we had nested monads and we couldn't compose them, and we needed monad transformers to be able to compose them. But what if I want to nest monad transformers so that I can compose the effects of mutable state, potential absence, and let's say asynchronism? What if I want all these three things? And another challenge is type inference, because it might not be obvious from the code snippets that I have shown, which are fairly simple, but often when you use a lot of transformers, the type inference gets in the way. And especially if you try to use nested transformers, then it just becomes a mess. So the more you nest transformers inside transformers, and the worse inference gets. And this is exactly the type of issues that CATS-MTL can be used, that CATS-MTL can solve. So here's an example of code. And by looking at it, it's unclear what it does. I mean, if you take a closer look, you can sort of guess what it does. But of course, it's very complicated. But the use case is very simple. It's just a function that takes a user and returns either a document or some error of type string. And we want access for users that are not administrators and don't have access to secret documents. And we want to have some mutable state, some counter that we want to increment on each attempt and maybe destroy the document when the maximum number of attempts has been made. And to do all that, I want to combine the effect of mutable state, asynchronism, failure, and maybe there is some reader T monad in here because, well, I don't even know what it does anymore, actually, but I'm sure it compiles. So anyway, so my point is this code is very complicated and it shouldn't be that complicated. So when we want to combine effects together, such as short-circuiting and mutable states, CATS-MTL can help us deal with all the type inference madness, all the type connotations that you need, all the boilerplates. And the idea of CATS-MTL is actually pretty simple. At least it's not very far from the idea of monad transformers. So MTL stands for Monad Transformer Library. And as you will see, if you're comfortable with monad transformers, then CATS-MTL is rather easy to pick up. So remember that monad transformers, they add some effect to a monad. And sometimes you want to be able to add multiple effects to one monad so that you can use all of these effects to model a particular use case. And CATS-MTL, instead of using monad transformers directly, CATS-MTL will encode these effects in the form of a type class. So you can write a program by adding sort of constraints to your effect type using type classes as the constraints. And by doing that, you gain the ability to combine effects together without the drawback of bad inference. So for example, the effect of raising errors is encoded in a type class that is called functor raise. And I can write this sort of program where I just have some f. I know nothing about this f except that it has an instance of applicative defined for it and an instance of functor raise. And functor raise takes two type parameters, the f monad that we want to add the constraint on, and some error type that will define the error type that I want to raise. So in that case, I want to raise strings in the context of my f type, and this is what this piece of code does. What about recovering? Well, there is another type class which is applicative handle, and applicative handle inherits from functor raise. So it has the ability to raise errors, but also the ability to recover them with a method called handle. And this method takes a function and then you can define what you want to do with the error that you have just recovered. And we still get a dedicated channel for technical errors because we have this ability to add a new constraint to our f type. So if I have a constraint on functor raise, for example, I can raise domain exceptions using any type, but I can also add a constraint on the type class called applicative error, which is from CATS, not CATS-MTL. And applicative error will encode the effect of raising and recovering errors. And I can say that I add the constraint to my f type, a constraint on applicative error that defines the ability to raise and recover throwables on top of maybe raising and recovering authentication errors. So how would we use that to model application use case? Well, once again, we start by rewriting the type signature of our smaller programs. I have omitted one of them, I think. And we say that these functions are defined for some f type that have a constraint on, let's say, functor raise. And it gives me the ability to raise an error of type wrong password, which is one of my authentication errors. Then I have other programs that I will also need to implement. And once I have these programs, I can compose them into an authentication method that has a constraint on funct arrays, because check password has a constraint on funct arrays, and maybe a constraint on applicative error also. So I have the ability to raise domain errors using funct arrays and the ability to raise technical errors using applicative errors, all in the same F monads. Awesome. This is the full code snippet. The GitHub project that I have linked on the Slack channel has all of the code snippets also in a Scala project. And now it is time to launch the application, interpret the program. So we had an abstract type F with some constraints on it. And it is now time to define what will be the concrete implementation of that type. And you see that the concrete implementation of a type F that has a constraint on applicative error and on applicative error and a constraint on applicative handle and on monad error is an ith, which is just a way of saying that CATSMTL defines type classes which are polymorphic variants of monad transformer. So monad transformer is the concrete type, and CATSMTL is the type class that you can use to use monad transformers in a more abstract style. And CATSMTL will provide instances of the CATSMTL type classes for all monad transformers, but also for nested monad transformers. So now that I have defined what will be the concrete F type, I can call my authenticate method and catch not only domain errors, but authentication errors. And that's it. So summing up, of course, errors happen. They are part of the software development, and when they happen, we need to handle them carefully. My main advice on that subject would be to have a clear distinction between purely technical errors, which are implementation details or connection errors, timeouts, that sort of stuff, and business rules, which are part of the user experience. And by using monad transformers, you can actually create programs that combine the effects of multiple monads. And by combining these effects, you have two channels for managing your errors, one for technical and one for domain errors. And CATSMTL, it's just a polymorphic variant of monad transformers that gives you this ability of combining effects, but with less boilerplate and less in a more easy way, especially when you need to nest transformers inside one another. There are plenty of error management strategies out there, so maybe CATSMTL is not the one for you. I feel that CATSMTL can be hard to pick up if your team members don't know monad transformers in the first place, and because it is this polymorphic variant of monad transformers, so it's easier to pick up if you're already comfortable with them. So maybe not rush into it. And of course, remember to have fun. And that's the end of this talk. So thank you for having me. And once again, all the slides and all the code examples are on my GitHub. And I don't know if I have time for some remarks or questions. I actually don't see the chats.
There was a few questions went by. There was one in the Q&A panel, right. Kind of two there. You can see it.
All right. What if you don't want to show circuit errors, but in aggregate multiple errors? Like a validated type class. Okay, so what if you don't want short circuit errors? That is a very interesting question. I actually don't know if there is a monad transformer that could encode. Maybe someone else can answer this.
Yeah, so in CATS, we have a data type called nested, which basically allows you to compose two applicatives together. So if you don't want short circuiting, that basically means you're bound to applicative. You can no longer have monadic flat maps. And that means, in essence, you can compose I/O together with validated using nested, and then use that for any kind of error accumulation. And it will just work. You won't need to write any code to kind of wire it up. You would just need to go from either T to nested. And I think there is a method that kind of like does some syntactic sugar, but yeah, it's definitely doable, and it's not hard either.
Wow, thank you for answering the question. I actually didn't know that. So, and there is another question about unrecoverable errors. How do you code your error handling so that you can know what exactly happened on a login attempt? It's an interesting question. I would say that some tracing solution helps. We had the talk from Jakub about tracing, which was very good. And as in fact, when I was working in my previous for my previous mission, we had this need of instrumenting HTTP4S services using Datadog. And at the time, I wrote a simple tracing library, which is just some functional wrapper around the Java Open Tracing API. And the fact that you are able to capture data such as the fact that you are able to capture data and measure every step of the program using some sort of tracing helps with that kind of debugging. And then typically in HTTP applications, when an unrecoverable error happens, or some technical error happens as part of the request, I would send an internal server error code to the user and log the entire stack trace and just forget the logs. But if you need something more powerful, then of course, I think tracing is the best option. And are monad transformers monads? So that's a tricky question because I'm actually afraid of of getting it wrong. But monad transformers are type constructors that operate on monads and return monads. And I think, but maybe someone else will be more qualified to answer this. I think that if your input monad, let's put it that way, is a lawful monad, then you will get back also a monad which is lawful in the same way. But of course, if you use, let's say, monad transformers on something like futures, then you get also all the drawbacks from futures that you have in the first place. Does that make sense? Is that correct?
Yeah, I think that's 100% correct. So if F is a monad, and then option T of F is also a monad. Yeah.
Yeah, that's what
exactly what you said.